Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to quickly wrap up our discussion on eigenvectors and eigenvalue and move on to the last section of the course, which is the least square methods. But before we talk about the least square methods, we need to talk about some of the prerequisite concept. We need to talk about orthogonal vectors. We want to talk about orthogonal complements of vector subspaces, vector spaces, and so on and so forth. And it's going to be a little bit theoretical at the end of the course. There's a lot of homework problems that involve questions asking you to prove this and that. But the good news is that we'll cover most of the proof in the videos. And computationally, once you understand the theoretical setup, computationally is actually pretty easy to execute the least square methods. So it won't be too much. It will be a little bit more involved, but it won't be, hopefully it won't be too overwhelming, okay? So let's quickly wrap our discussion on eigenvectors and eigenvalues. So if you have a square matrix, so this is n by n, and if you can find a non-zero vectors, this has to be non-zero. So this has to be non-zero vectors such that you have this. This is a number. This is the real numbers, and this can be zero. This is what we call eigenvalue. It can be zero, but the eigenvectors has to be non-zero. So if you can find numbers and also vectors such that you have this, then we say that this v here is eigenvectors. This lambda here is an eigenvalue. Some of you asked this question in the Piazza that whether or not this lambda here can be a complex number. The answer is absolutely yes. And the only things that we will not do is to deal with all this kind of situation in this course. But you are absolutely right. It's very easy to get into a complex eigenvalue, and the corresponding eigenvectors can also be complex. And so we'll be in Cn instead of Rn. So this is the things you want to talk about. So in this course, everything will be real. But as you know, I can give you a very simple matrix A where the determinant, let's say, is 2 by 2, and you compute the determinant of this matrix, which is to try to find a characteristic polynomial. And what you get is lambda squared plus 1 equal to 0. Then you know that this eigenvalue has to be complex numbers. And correspondingly, we'll be looking at the situation where we'll be in C and Cn, and this is the things that you will study in advanced linear algebra, but not in this course. But you're right, absolutely right. So lambda can be actually a complex numbers. And so we won't be doing all that. So that is easier for us in terms of computations. If you have complex numbers, the computation will be a little bit more tedious. Okay, so the things I wanted to talk about in these notes is that this notes actually contains some theoretical result. You don't, if you're interested, you can look at the proof, but I would not require you to be able to prove all this. But let's look at some of the result, which is pretty useful when it comes to looking at the eigenvectors and eigenvalue. And as you recall from the previous video, the main thing for us to find the eigenvectors and eigenvalue, which is very useful, you will see that in physics a lot. You will see that in statistics. You will see that in engineering. You will see that the application of eigenvectors and eigenvalues in various contexts. And in mechanical engineering especially, there's a lot of computation involving use to find the eigenvectors and eigenvalues. And for us, and actually for a lot of applications, the main reasons we use eigenvectors and eigenvalue is so that we can diagonalize the matrix. We can use the eigenvectors to help us diagonalize the matrix. And you can see from the previous video, sometimes that is not possible. And the thing is that in order to diagonalize a matrix, we need to have enough eigenvectors. We need to have enough linearly independent eigenvectors. And this theorem here is try to help us to determine when we can have enough linearly independent eigenvectors, so to speak. So it says that if you have distinct eigenvalues, if when you are computing the characteristic polynomial and you have all this distinct eigenvalue, the corresponding eigenvectors for all this distinct eigenvalue will be definitely linearly independent. So if you have lambda 1 equals to 1, lambda 2 equals to 5, and lambda 3 equals to 7, let's say, so the eigenvectors corresponding to this and eigenvectors correspond to this, eigenvectors correspond to this eigenvalue, they are all linearly independent. That's what it says, because these are different. Okay, what happens if you have repeated eigenvalue? So what happens when you repeat eigenvalues? That's a little bit different story now. So that will be answered by this second theorem right here, which says that if you have lambda eigenvalue lambda 1, lambda 2, and lambda 3, and if you within this lambda 1 you can find up to p independent eigenvectors, and within this lambda 2 you can find up to q linearly independent eigenvectors for this particular eigenvalue, so on and so forth, and all the ways to, let's say, you can find all the ways to r linearly independent eigenvectors for this eigenvalue. And if you put them together, this is actually going to form a linearly independent set. So all these vectors here will be linearly independent. That's the theorem. So somehow we can still manage to see in what situations we can actually have linearly independent eigenvectors, but there's no guarantee that we will have enough. This is just kind of like a theorem that says that, hey, don't worry too much. If you see this, then we'll have linear independent eigenvectors. But again, whether or not we have enough eigenvectors to diagonalize a matrix will depends on the geometric multiplicity, right? So if it is size n by n matrix, the matrix is diagonalizable if you can find n linearly independent eigenvectors. So here we didn't know the size of a matrix. We didn't really know. This theorem is not used to diagonalize a matrix. This theorem just says that, hey, if you are worried about linearly independent, then we actually have this. We can guarantee that these are linearly independent. But is it enough or not? Well, it depends, right? If altogether here, if A is n by n matrix, and altogether here you have n linearly independent eigenvectors, then diagonalization is possible. But as you can see from previous videos, that they are a very simple example of a matrix that's just simply not diagonalizable. And how to deal with not diagonalizable matrix, that is, you will learn something called a Jordan canonical form. You call Jordan's canonical form, which is that we don't go for diagonal matrix. Diagonal matrix is the best matrix that we can get, but if we can't get it, we go for the second best, which is a matrix that is kind of like diagonal, but not really diagonal. You might have an entry that is off diagonal, something that looks like this, for example. And so you have something that is like on the off the first diagonal. So this is not ideal, but it is still better than nothing. So if we don't have enough eigenvectors, we'll have to talk about something called a Jordan canonical form, which is again something that we will not cover in this course. Okay, just an FYI, sort of, to like, if we don't have diagonal matrix, we will go and look for something that is called Jordan canonical form, Jordan matrix, and all that. Okay, so one last thing, which is a very nice theorem, and that will be everything I want to say about eigenvectors and eigenvalues. So there's one last thing I want to talk about is this theorem here, which is known as the spectral theorem for symmetric matrices. So if you have been following along the 4 videos on eigenvectors and eigenvalue and part of the discussion that we have so far, we are mainly, by now you should know, we are mainly concerning whether or not a matrix is diagonalizable. So if a matrix A is diagonalizable, it's good, right? And what is the meaning of diagonalizable? Matrix A is diagonalizable if you have invertible matrix P, right, such that P inverse A, P equals to D. And the question is that if you look at all the matrices out there in the universe, what type of matrix you can guarantee that diagonalization is possible? And we have a very simple answers to that. And the matrix is not something that's super weird or anything. There's a class of matrix that we know is definitely diagonalizable, and that is given by this theorem. This is called a spectral theorem for symmetric matrices, which says that if you have a symmetric matrix, if you still remember, symmetric matrix is those matrix that the transpose of the matrix equals to itself. So symmetric matrices are things like, so let's say 2 by 2 symmetric matrices will be like 1, 3, 5, 5. This is a symmetric matrix. 1, 2, 3, 4, 4, 3. Yeah, we already have a 3. So let's say a 5, 5, 0, 0. This is a 3 by 3 symmetric matrix. That's like, this is kind of a reflection. This is like the axis of refraction, and everything off the axis of reflections, the number has to be the same. These are symmetric matrices. A, if that's A, your A transpose will equals to A. So if all these entries are real, then we will call this kind of matrix, symmetric matrices, as real symmetric matrices, right? So spectra theorem for symmetric matrices says that if your matrix is symmetric, then it is definitely diagonalizable. And in fact, there's more things. We also know that the P here, there exists a P such that P inverse AP equal to D. Actually, we also know more about the structure of P. In fact, all these matrix P have, if they are orthogonal matrix. Orthogonal matrix means that if a matrix is orthogonal, it means that Q transpose times Q is actually equal to identity matrix. If Q is what we call orthogonal matrix, then Q transpose times Q is equal to I, and that means that Q inverse is actually Q transpose. So these are called orthogonal matrix. So there are more things that is in it. You can look at the notes, but key idea from this theorem it says that if you have a real symmetric matrix, it is definitely diagonalizable. Those are matrices that's definitely diagonalizable. So these are the notes which you will get. It's available on Blackboard. These are all contain a lot of theoretical result. There's a lot of proof in it. But if you don't want to read the proof, that's fine. I would not ask you to reproduce this proof in the exam. And so you even if you do not know the proof, at least you should know the statements of the theorem, what the theorem tried to say. And especially you need to know that we have one class of matrices which is very nice. They are definitely diagonalizable, and that particular class of matrices are real symmetric matrices. Okay, so that's called the spectral theorem for symmetric matrices. It's one of the very important theorem in linear algebra. Okay, so we are done with the linear algebra. So we are, I mean, not done with linear algebra, I'm sorry. We're done with eigenvectors and eigenvalue. And now we are going to look at chapter 6. So we are going to build up enough concept and terminology so that we are able to develop and set up the least square methods at the end of the semesters. Okay, so now we're just going to go a little bit slow. We're not going to do something super fancy today. We are going to use this opportunity to do some review. And the things we're going to talk about right now is dot product. So we have seen it before, actually. If you have taken Calc 3, and actually Calc 3 is a prerequisite for this course. I mean, you can take it concurrently, but it is the prerequisite, and dot products is something that you are familiar with. So remember that when you have matrices, so when we have matrices, say matrix A, matrix B, we can add, we can subtract them, we can scalar multiply them. And when we multiply them, we have two choices. There's something called the cross product, and another is called the dot product. So one of the things about dot products is that it is actually pretty easy to do, and the definitions of dot products is given here. The key thing is that if you have all these column vectors, these are in Rn, if you take the dot products, you would not get another matrix, you will get a numbers. And the way we compute dot products is straightforward. You take these components, multiply them, and then at the end, you sum them all up. So this is how you compute dot product. And from here, you can see that the dot products of two vectors obviously is a real number. This is just a numbers. And if you still remember from physics or from Calc 3, that when we talk about vectors, there are several things that is critical, right? So vectors is a mathematical objects that has two things on it: directions and magnitudes, right? So if you have a vector v, we can talk about its directions, and the direction is given by the unit vectors. So we can take tangents, theta, whatever, and find out what's the directions. But we can also figure out what's the magnitude of the vectors, and the magnitudes of the vectors is given by, we use this notation, is given by square root. Okay, so if your v is in Rn, so you have v1 all the way to vn, and the magnitudes of these vectors is v1 square all the way to vn square. Sum them up and then take square root, which is here, which is here. And we can also get it by taking the dot products of these vectors, v by itself, because if you take the dot products of v by itself, you get v1 square all the way to vn square. So this magnitude is nothing but the square roots of this dot product. So these are the things that you should know by now. This is not supposed to be something that you haven't seen before. And just want to quickly remind you, these are the properties of dot products. They are symmetric. U dot v and v dot u is the same. You can distribute your u. When you take u dot v plus w, you can distribute. You have distributive properties. And one of the things is that when you have scalar, you can do this. And also we have something called the positivity property. That is the v dot v is never negative. So it's non-negative. V dot v is non-negative. It's very easy to see it because they involve the sum of square. And it cannot be negative, but it can be 0. And when it is 0, we know exactly when it is 0. It is 0 when v is 0. So this is if and only if. So if the dot product is 0, then the vector itself is a 0 vectors. If the vectors is 0, then the dot products is 0. So this is the positivity property for dot products. And we can talk about the angle for vectors. So if we have, again, this is something that you have seen before in Calc 3, but we're going to say that again. So if you have vector u and vector v, so let's say they're in R3 because we can still kind of imagine it. So this is angle theta. So if they have angle theta between these two vectors, this angle theta can be actually computed using these formulas because u dot v actually can be also shown to be the magnitudes of the vector u times the magnitude of the vector v and cosine theta, where the theta is the angle between these two vectors. So we're not going to prove all this here. I'm just going to give it as a theorem. And so u dot v can be computed in two different ways. So u dot v, by definitions, you can compute it like this, right? And as a theorem, we can show that u dot v computed this way, is actually equals to the magnitude of the vector u times the magnitude of the vector v and times the cosine theta, where theta is the angle between these two vectors. That is how we can use the cosine theta to compute what's the angle theta between these two vectors. And most of the time, we don't really care when they make a 45 degrees, 64.5 degrees or whatever. It is very important when actually they are 90 degrees to each other. So if you have two vectors and they are 90 degrees to each other, those are the vectors we call orthogonal vectors. They are orthogonal vectors. Orthogonal vectors are vectors that are perpendicular to each other. And when your angles is 90 degrees, you can see that cosine 90 degrees is 0. So when your angle is 90 degrees, then the dot product will be 0. And when the dot product is 0, your vectors is orthogonal to each other. So we define orthogonality like this. And again, even though we are saying this in R3 so that you can easily imagine it, but all this concept extends all the ways to Rn. So, I mean, we can't really imagine what happened in this space, but everything that we know for R3 is extended forwards for all the possible Rn. So in mathematics, we don't care so much about whether or not we can imagine the space. In physics and all that, you do, because it represents a real system in the world. So if you are talking about, it takes forever for Einstein to say that we have the concept of space-time. So we are in R4, we have the R3, and then have another dimensions of time. And for physicists, R4 is that's it. They cannot do R6 or R7. That's the reason why people keep making fun of string theory, which they require higher dimensional space, but we don't see them. But in math, we don't really care about this. In math, we can freely talk about R to Rn, where n could be any big number. It doesn't really matter for us. So what I'm saying is that the concepts here about angle between two vectors can be extended to more than R3. So as you can see in this notes here is that this angle between any two vectors in Rn actually still computed the same way. We don't, even though we can't imagine it, but we can still compute the angle theta. Okay, so this concept of orthogonality is critical. It means that two vectors are perpendicular to each other, and we can tell when two vectors are perpendicular to each other or orthogonal to each other, and we can tell by looking at the dot product. So if the dot product of two vectors is 0, this is a good case. We know that the vectors are orthogonal. So let me show you one thing why it is a good thing that the matrix is orthogonal. So let's look at it here. Okay, so let's look at it here, and let's get rid of this. So let's give you a very quick example of why orthogonality is important. So let's say you have vector u, you have vector v, they are in R2. So let's say they are orthogonal vectors, which means u dot v is 0, right? So these are orthogonal. So these are orthogonal vectors. Now, I claim that if you have orthogonal vectors, they are linearly independent for sure. So my claim is that u, v orthogonal, if they are orthogonal, okay, i.e. their dot products is 0, okay, all right, then u and v, these two vectors, are linearly independent. They are linearly independent, okay, and you can extend it to 3 or 4, doesn't really matter. I'm just giving you a very simple example here. So how do you know that? How do you know that if you have two orthogonal vectors, they are linearly independent? So how do you check linearly independent anyways? You check linearly independent by doing the same thing. There's only one thing you would do. That's you set k1u plus k2u, k2v, and set it equal to 0 vectors, and try to solve for the k1 and k2. If k1 and k2 are both 0, then they are linearly independent. If k1 and k2 are not 0, and you can still have this, then u and v are linearly dependent. So everything is still the same, nothing really different. Okay, so how do we know that if they are orthogonal, if u and v are orthogonal, they are linearly independent? So let's solve this. Let's solve for k1 and k2. But usually, last time, the way we solve it, we have to set up a linear system and REF a matrix, blah, blah, blah. We don't have to do it now because we have more tools. So let's take this entire thing, okay, and let's take the dot product. So let's say I take u dot this entire thing, and so I take u dot this entire thing on the left and on the right. So u dot 0, this is a 0. This is a real number 0, not a matrix. Okay, and here we can distribute. So using the properties that we know from the previous theorem, so we can take the constant out, and we have u dot u, and then we have k2, and then we have u dot v, right? And then we have the number 0. These are all number now. Everything here is a number, okay, no longer vectors. Okay, so these are the number 0, okay? So u dot v is 0 by definitions, right? So u dot v is 0 by definitions of uv are orthogonal, and I forgot to mention here, this uv here are non-zero vectors. This uv here are non-zero vectors, okay? Because if you have 0 vectors, they are definitely not independent, that's for sure. So this is, forgot to mention it, but uv here is assumed to be a non-zero vectors. If you have a 0 vectors, the system is never going to be linearly independent. So implicitly, uv are non-zero vectors. So where do we use uv are non-zero vectors? Right here. So if your u is a non-zero vectors, your u dot u can never be 0. How do we know that? We know that from the positivity theorem, the properties right here. So if your vectors is not 0, the dot product will not be 0. You can also see it pretty easily by taking the dot products, right? So u dot u will be kind of like u1 squared plus u2 squared if your u is u1, u2. And you can see that if your vectors are not 0, this terms is never equal to 0. So you can see now back to here, you have k1 and a non-zero number and equal to 0. So this is a non-zero number. And that means that if you have two numbers, one of them is non-zero, multiply together, get the number 0, your k1 has to be 0. So now we know that if you have this thing set up, your k1 actually has to be 0. So by doing that, by setting up k1, by setting up the usual equations, okay, k1u plus k2v equal to 0, and try to solve for it, we can see our k1 has to be 0 if you take the dot product, with u. And you can easily see that if we repeat that process by taking the dot products instead of with u, but now we are taking the dot product with v, you will get k2 equal to 0. So let's do that again. So k1, all right, so u, this is the vectors, k2, v, this is the vectors, this is 0 vectors. Okay, so now you take the v, dot product with v, right, dot products with v. So here, this is the number 0. Here you distribute, you have k1 v dot u, k2 v dot v, and then you get the number 0. Again, this is a 0 because u dot v and v dot u is 0. Why? Because we assume those vectors are orthogonal. And here v dot v is a non-zero numbers, so you can again get k2 has to be 0. So if you set up these equations, you will see that the k1 and k2 has to be 0 if the vectors are orthogonal. Let me say that again, non-zero vectors and they are orthogonal means that if you look at these equations, the constants k1, k2 has to be 0. That means by definitions, the uv is independent. So the uv is independent. So these two vectors are linearly independent, which means that every time if you're in R2, okay, this is our y, this is x. So if you have a vectors called u, you have another vectors called v. If they are linearly independent, so if they are orthogonal, then they are linearly independent. Okay. In particular, you can see that your I and j are linearly independent. We know that already. I, j, right? This is your j. That's your I. Your I and j are linearly independent. They are orthogonal. I and j are obviously orthogonal. I and j are obviously orthogonal. I hope you can see that. This is your I, this is our j. If you take a dot products between I and j, you get 0. Okay, so they are orthogonal. So I and j are orthogonal. Okay, and they are therefore linearly independent. And actually, not for I and j, any vectors you have v, you have another one v. If they are orthogonal, then they are linearly independent. So and the proof for that is not very difficult. So you can see our orthogonality is pretty nice. It's something that we haven't really fully explored yet until today. But when you have vectors that are orthogonal, they are linearly independent. So the concept of orthogonality is not too difficult. It just means that the two vectors are perpendicular to each other. They are 90 degrees to each other. And we can have all this nice property. We'll come back and explore these kind of properties in the future. But we just try to using plant the seed, right? Like inception. So just kind of give you this idea right now. So that in the future, you'll remember, say, oh yeah, last time we talked about that before. Okay, all right. So orthogonality just simply means that two vectors are 90 degrees to each other, which means computationally, which means that the dot products is 0. Okay, the dot product is 0. So dot products of two vectors is equal to 0 is a good thing. It's a good thing. Okay, the dot product of two vectors equal to 5. It's like, oh, I don't care. It's just like whatever. But the dot products between the two vectors are 0. It means like, oh, they are orthogonal. It's a good thing. One thing you can say immediately is that those two vectors are linearly independent. That's one thing you can say. Okay, so one of the things that we want to do right now is to look at the concept of projections. We have seen this before many times. Actually, one of the sections I actually showed that in class. How to derive these projections formulas, and it is pretty straightforward. And you do that in your homework as well before, so hopefully you still remember. So the projection of a vector, so if you have a vector A, right, and then you have a vector X, and you want to project, okay, you want to project this vectors X onto A, so you want to figure out how big is this vectors. That is called the projections of the vector X onto A. That's the notation. So what is this? This is a vector. So this is a vector, all right? So the vector, every vector has two things that we can talk about: the magnitude and the directions. So where, for this particular vectors, where is it pointing at? So they are pointing at, the directions will be in the directions of A. All right, so it will be in the direction of A. All right, so projection of X onto A will be in the direction of A because you project it to A. So it will be in the direction of A. Now, what is the magnitude of this vectors? The magnitude of this vectors is exactly this length right here. This length right here. So it's easy to imagine, let's say this is in R3 or R2. So let's do it anyway. This is like, imagine this is like we are in R3 or we are in R2. So they kind of like form a 90 degrees. Just draw this thing down. You see it's 90 degrees. and you have to figure out how big is this. So how long is this? Okay. So if you can figure this thing out, you will get this formulas. And we have proved this before. And let's do that again. Okay, let's do that again here. So it's not too tricky. Okay, so let's compute this. So let's introduce an angle theta between x and a. So so this is a vectors that has a magnitude and a direction. So the directions is in the direction of a. So when something is in the direction of a, we're going to communicate that by using a unit vector. So this is called unit vectors. Okay, it's a vectors of a, but if you take the magnitude of these vectors, it will be 1. So unit vectors is very good for us to identify the direction. So this is a 1 unit vector. It's a vectors with unit 1 and pointing in the direction of a. So if you figure out the magnitude, you take the magnitude, multiply this unit vectors, you will get this vector. So this is a very typical concept in physics and all that. So hopefully this is not the first time you've seen it. But this is how we construct a vectors. We have to figure out the magnitude of the vectors and this direction. So this is magnitude. Okay, so this is magnitude and this is direction. Okay. All right, so what's the magnitude? So magnitude is how big is this? So how big is this? All right, so as you can see from basic trigonometrics, using basic trigonometrics functions, so this is a vector x, right? So here, this is magnitude x. This is the magnitude. This is how big, how long. If you can actually physically take a ruler and measure it, this is the magnitude of x. So this part here, how big is this? This is actually x cosine theta, right? Because when you take cosine theta, you will take that value divided by this hypotenuse. So let's say you don't know. Let's say we call it x. Okay, we have too many x. Let's call magnitude. Let's call it m. This is a number, all right? The length, right? So cosine theta will be m over this. Okay, so what is m? M will be cosine theta multiply this. So this is the magnitude. So this is correct. This is what we need. This is what we need. We have the projection formulas right here. That's our projection formulas right here. That's our projection formulas right here. Okay, but this is not quite useful because most of the time we don't know the angle of these two vectors. We know most of the time, what do we know? We know x, right? X will be like x1, x2. We know a. What is a? A will be a1, a2. We don't really know the theta between these two vectors, but what we know is this two. So we want to make this more useful. So here, remember that if you take the dot products x dot a, this is given by the magnitude of x times the magnitude of a cosine theta. So you will see that this thing is very, very close to the dot products. It's very, very close to the dot product. So we can change this into a dot product. We can change this into a dot product. And how we do it is we do the makeup method, right? So I'm going to rewrite this. So I'm going to have the x. Okay, this is obviously a vectors x cosine theta. So I am going to put an extra number here, and I'm going to divide this extra number here. Okay, yeah, assuming a is not a zero vectors, otherwise this won't work, right? So this is a, and then this. So we are this is still the directions, the magnitude. I'm just changing it a little bit, and that you can see this on the top is actually the dot products of a and x, and the dot product of a and x is easy to compute, right? So this is x dot a, right? And this a and this a make a square, right? And then this is a. So this is the projection formula. This is the projection formula of x onto a. We have derived this many times before. I am doing it here again. So this projection of x onto a is given like this. And the derivations in order to prove it is actually very straightforward. You just need to figure out the magnitude and the direction. And computationally, this is easy to compute because, as I said, most of the time, your x is given like this, x1, x2. Your a is given like this, a1, a2. And all these are computationally easy. We can just multiply everything out to get this. We know this, we know this. Everything will be cool. We don't even need to know the theta because we don't need that anymore. Okay? So that's the projection formulas. So that's the projection formulas. So this is true in R2 and R3 where we can see it, but it's still true in Rn. We just extend it, which is like, oh, in R5, just the same thing. We do the same thing. In R6 is the same thing. In R1000 is the same thing. Okay, so we have the projection vectors. So the projection formulas is given here. So that's the projection formulas. Now, one last thing before we'll finish this discussion here, is let's do one more computations. So if you look at these pictures right here, so we have A, right? And then we have X, and then we have the projections, right, of X onto A, right, which is this vectors. And this is now a very simple question that I'm going to ask you. So if this is X pointing this way, this is a projections, right? So what is this vectors? What is this vectors? All right. So if you have taken physics, this is something that is very simple. I mean, if you're at IIT, you know these answers. Okay. So this is vector additions. How do we add two vectors? So remember, if you have a vectors, let's say P, right here. Let's say you have a vector Q, which is here. So this vector P plus Q, right, is going to be right here, P plus Q. So P, Q, this is P plus Q. That's how we add vectors, isn't it? So one way to figure out what is this vectors is to ask the same thing. Let's say this is Q. This is vector Q. So we have projections X onto A plus Q apparently equals to X. So your Q is X, right, minus the projection vector. So this one right here is X minus the projection vectors. Okay, that's how you get this. Okay, and you can double check. This vector plus this vectors obviously give you this vectors. Okay, so here, so we have X, we have A, we have projection of X onto A, and we know this thing here is X minus projection of X onto A. Look at this one right here. So what we're going to prove right now is that this vectors is actually orthogonal to this vectors. Okay, this vectors is orthogonal to this vectors. I put a 90 degrees here because I already verified that. But before I verify that, I can't really know this is a 90 degrees. Okay, so right now, I want you to see this. You have this vector, we have this vectors, and I'm claiming that these two vectors are 90 degrees to each other. They are orthogonal vectors. How do we do that? Well, the only thing you can do, I mean, the easiest thing you can do to check whether or not two vectors are orthogonal is to take this vector and take the dot products between these two vectors. So that's what is shown here. Okay, so you take this vectors and this vectors, they are vectors, and take the dot products. So when you take the dot products, we apply a lot of properties that we learned from before. So for example, we can distribute. So you can distribute this here, here. So that's the reason why you have this dot this and this dot this. And then you write out the projection vectors. So this is a projection vectors. You write everything out. So you write everything out. Your projection vectors is this. Your projection vector is this. Your projection vectors is this. So be very, very careful. This is just a number. This is just a number. This is just a number. And when you have a number, you can just take the number out. You can take the number out. How do we know that? Right here. All right. So we can regroup them. If this is the numbers, KAU, you can take the number out. Okay, you can take the number out. You can also, why do we have that property? You can also just think about it. Like this is all together, these are just number, and these are common factors among all these numbers, and you can take them out just like factoring them out. So these are just number, these are just number, you can just numbers. So you can see right here from our computations. Okay, so here you take it out. This is just X dot A. So this is just X dot A. So here, if you factor this thing out, put it in the front. So let's put it in the front. This is X, this is A. So this is X dot A. This one here and this one here, just put them outside here. So the only things that you do, the dot products A dot A. Now, so A dot A is the magnitude of A squared. A dot A, that's magnitude of A squared. Okay, so this thing here will cancel with one of this. So what you have for this part is nothing but this. And what you have for this part is nothing but this. Okay, and you can compare and see they are the same thing. They are the same thing. So you can see that this is a subtraction of the two numbers, and they are 0. So now we can see, just go through this very carefully. It's not a very difficult computations. Just go through this very carefully. This is the big idea is you take the dot product. That's it. The big idea is to take a dot product and show that the dot products of this vector and this vector is 0. So now we can verify that this vectors and this vector, they are orthogonal. So we can write X as something as a projection vectors plus something that's orthogonal to it. So this is a type of projection theorem. You might not know what projection theorem is right now, but you can see for every vectors, we can write as a projection plus something that is orthogonal to that projections. All right, so if you have a vector X, any vector X, we can write as a projection vectors plus something that is orthogonal to it. Sorry, this is x. So you can write x as a sum of two vectors, p, q, for example, where p is q, p plus q is x, and p, q are orthogonal. This is what is happening right here. So any vectors x that is given in Rn, you can write it as the sum of two vectors p and q, where this vector p and q are orthogonal to each other. We have they have application in the future, but right now we're just doing nothing but applying the dot products and be very naive and like, oh, they are orthogonal. We will see in the future this is going to come up again, but right now we're just practicing on how to compute the projections. This is a review. And how do we show that when we have this, we can figure out what this vector is, and we just shown that these two vectors are actually orthogonal to each other. So that's it. This is the things I want to say in this video. So in this video, we have a slight review. We review a little bit of the eigenvectors and eigenvalue problems, and we wrap it up, and we introduce the concept of dot products. Very simple concept, dot products, angle between these two angles. And then we use that to say something about orthogonality. When two vectors are orthogonal to each other, it's good because we can say that they're linearly independent vectors. Okay, orthogonality, if you have 90 degrees, two vectors are 90 degrees to each other, they are definitely linearly independent. You cannot write one with another vectors. This is actually a pretty easy concept in physics. You know that if two forces are 90 degrees to each other, they can contribute, right? It says they have no effect to each other. They are separately. They are linearly independent. You cannot write another vectors as the linear combination of all those orthogonal vectors. And here we can see this application here, and we will wrap this up. We will say that this is the end of this video, and we'll come back to it in your homework. And in the future, we'll talk more about all this concept. It's very critical because in the study of least square methods, there's a lot of concept on orthogonality, and we have to get familiar with this concept. All right, we'll see you in the future videos. Thank you.